There's only one minimum or maximum. There's only one extrema. So we can find the minimum value of the gravitational potential energy relatively easily. this local minimum, that is. Oops. We can find it relatively easily, if only because we can just take the derivative, set it to 0, and solve. So the effective potential, and let me just make sure that I get this right, it's L squared over, I want to say it's over 2 m e, this would be the mass of the sun, sorry, r minus g m m, that's the mass of the sun, times the mass of the Earth over r, and that should be r squared. Sorry. No, you might be right. That might be the mass of the Earth. I need to go and double check my notes. No, this lecture is being recorded. I can never remember these things either. That's why it's okay to use open notes. Anyway. Yeah, no, so I wasn't recording the chunker. Sorry about that. Two m r squared. Yeah. Okay, so this is correct. Right. I don't know if they're typically open note, but they have been in my experience. Actually, no. When I took physics a lot, I didn't have a whole lot of open note. Anyway, right. So this is the effective potential. I always have to look this up because it's just getting these factors right can be challenging. Right. Okay. So what we're going to do is let's just take the derivative of this and set it equal to 0. So, oh, I had it right there. So the derivative of the effective potential as a function of r, this is distance from the sun, this would be minus 2, so that would cancel the 2 in the denominator, so it's minus L squared over me r cubed plus gm ms me over r squared, right? And we just want to set this equal to 0. Now we can multiply through by r and get 0, or we can multiply through by r squared rather, or even r cubed, just to simplify things. And we'd get that we're going to multiply by r cubed. Get that g ms me r equals L squared over me. So this is the place where it's minimum, right? When you solve for r here. So r in that case is just equal to L squared over g ms me squared. Looks right to me. And so you could have plugged in and solved. I have that calculation already ready. And you end up with r is equal to 1.495, let's round properly, 1.496 times 10 to the 9th meters.
Can I ask a question about that real quick?
Yeah, sure.
So when I was calculating the other part, you had to calculate like the semi-major axis of the Earth's orbit. And I noticed it was almost the same number for the formula in part A.
Oh, the eccentricity? Or using the eccentricity?
For the angular momentum, I used the formula that you gave us. So anyways, I calculated the semi-major axis and it was very, very close to this answer. Is that because the Earth's orbit is almost circular?
Yeah, I mean, so if you look at the aphelion and the perihelion, both those numbers were given. One was 147.1 gigameters. One was 152.1 gigameters. This is about halfway between the two, which just says that in an elliptical orbit, if you take this distance, if you take the average of those two distances, which would be somewhere like here-ish, that would be when you're moving fastest towards the center. But yeah, I mean, basically all these numbers are going to be close because it's nearly circular.
Okay.
Let me finish getting through 3, and then I'll talk about 2. Yeah, I'm sorry, that should be 10 to the 11, not 10 to the 9. Yeah, so the way I calculated L squared was just by using the formula that L squared is A times 1 minus E squared mu sub S mass of the Earth squared. So this is, let me put it in variables that we used here, G M sub S M sub E squared. You can just plug that in. And so we could have just plugged that in directly, and then we would have canceled out these two terms, and we would have just gotten A times 1 minus E squared. And the way that you calculate E basically is just involved, or the eccentricity is just involves a little bit of geometry by noting that the semi-major axis is related, is equal to the perihelion distance plus the aphelion distance divided by 2. And then you can figure out how the aphelion distance relates to the eccentricity and so on and so forth by using the elliptical geometry. Anyway, so this is the number that you get for the distance. And now we don't really need much of anything else. Let me, actually, so we will need L. So let me write down what L works out to be. L works out to be 2.66 times 10 to the 40th. And then what units does L have? It has units of momentum times distance. So it has units of kilograms meters squared per second. How would you know which gravitational parameter to use? I don't understand. So I used mu in my shorthand calculations because I know that you can replace GMS with mu sub S, but the formula just involves GM. I don't know if that helps. So that's what L is. So we needed L, we needed R. What else do we need? We need these quantities. So I'll give you those two. GMS, which is the gravitational parameter of the sun. This is 1.327 times 10 to the 20th, and I think that that's meters cubed per second squared. Let me think about that for a minute. No, that can't be right. It's newtons. So it should be newtons times Newton meters, newtons divided by, so newtons times meters squared divided by kilograms. And so kilogram meters per second squared would be, oh, it is just meters per second. It is just meters cubed per second squared. Okay, I was right. All right, so this is our gravitational parameter for the sun. And then we need the mass of the Earth, which is clearly in kilograms, which we have as 5.974 times 10 to the 24th kilograms. All right, so we need all of these numbers to calculate, to do part 3C. Right, so part 3C is now saying, okay, so what would happen if we were to plot the distance of the distance that the Earth is from the sun, R, as a function of time? Well, we know that when the Earth is closest to the sun, it will be, say, a distance, that's perihelion, so 147.1. I'm going to drop units here just to make it easier. And when the Earth is furthest from the sun, it'll be 152.1 units. And then it'll oscillate between the two because it gets closer and then further away and then closer. And it turns out, because the Earth's orbit is approximately circular, it'll look something like this. And so if you were to plot this, you might say, oh, that looks familiar. In fact, that almost looks like harmonic motion. It almost looks like sine. And because of that, you would think, and this is what I tell you in the problem, that it suggests that we can approximate the radial distance, or we can model the radial distance as if it were a simple harmonic oscillator to a good approximation. Now, it's not truly a simple harmonic oscillator, it's just close, but it would be a good model. And so what we do, like we did on the last lecture on Monday, is we take we write down what our total energy is again. So our total energy is 1/2 the mass of the Earth times the radial velocity squared, or put a different way, This is dr dt squared plus U effective as a function of r. Now, so already this has almost the right form. It has 1/2 times some effective mass, in this case it's just the mass of the Earth, times the derivative of something squared, and then there's just a function of that something. If we can write that function as a quadratic, then we can approximate it. We can approximate the system as a simple harmonic oscillator. So what we want to do is we want to approximate the effective potential energy as a, or using the Taylor series. Now the trick here is we want to approximate it. We want the approximation to be valid for the regions or for the values of R that we care about. We care about the value of R when it's 147.1 gigameters. We care about the distance. We care about the value of U effective of R when it's 152.1 gigameters. And so it turns out that the best place to approximate this, and indeed this is the sensible place because, well, the best place to approximate it would be where exactly in the middle. Sorry, that wouldn't be the best place to approximate it. That would be a place to approximate it. But even better, we know for a simple harmonic oscillator, yeah, that graph is this graph is, sorry, this graph is R. Over R with respect to time, not U effective. U effective is like this. So the point is we know for standard simple harmonic oscillator, a spring, that this mass is moving the fastest when it passes through its equilibrium point. So what we'll do is we will expand our effective potential energy about that point where the mass, which is the Earth, is moving fastest. And we already calculated where that is. So this is the point that we wish to expand about. Because at that point, in our approximation, the potential energy will be 0, and the kinetic energy will be at its largest, because that would be when it's moving the fastest. So that's why we choose that point to do our Taylor series expansion. So now we just have to write an approximation for the effective potential of R. So, and we want to expand about R equals R naught, which is what I labeled here. So this would be equal to the effective potential at, or this would be approximately equal to the effective potential at R naught plus the derivative of the effective potential at R naught times R minus R naught. I'm just doing the Taylor series now. Plus the effective potential, the second derivative of it, evaluated at R naught, divided by 2. No, there are no lecture notes for this. Times R minus R naught squared. And we could keep higher terms, but as long as one of these two terms is not 0, then we'll be good, and we cannot worry about the higher terms. In fact, we actually would hope that this term is 0, and then this, the second derivative of the effective potential at R naught, that should be the effective spring constant, because we already see that it would be multiplied by a quadratic thing, and it's divided by 2. Now let's check that. So first, we don't care what this value is actually at all. Like we don't care what it is at all, it's just a number. So I'm just gonna leave it as that. So this is equal to UF, I'm just gonna keep it plugged in. Now, what is the derivative of the effective potential evaluated at R naught? Well, think back to how we figured out what R naught was. By definition, we solved for R naught. We solved for R naught by setting the effective potential equal to 0. Right, so that second term is 0. So that's just 0, so we ignore that. And then we just have to figure out what the second derivative is. So this is just this guy, again, over 2, and then R minus R naught squared. And we don't have to keep any other higher terms. This should certainly not be 0, because this is not if you guys remember from pre-calc, the second derivative would be 0 when it's a critical point. And a critical point usually implies that the derivative is 0 and that it changes from concave up to concave down at that point. But if we look here, it's just straight concave up the whole way through at that minimum value. So we know that the second derivative should be positive, and in particular not 0. So it's just whatever that number is, and we can go and we can calculate that in a minute. But the whole point of this problem was to figure out what the spring constant K is, or what the effective spring constant is. So let's now write down our total energy. This is equal to 1/2 me times the time derivative of r with respect to t squared plus u effective r naught. This should be an approximately equal to, plus u effective r naught divided by 2 times r minus r naught squared. Now, this doesn't look exactly like the spring potential or the spring total energy, but keep in mind, this term is just a constant. It's just a number. And because this is a potential energy, we can just subtract that number from the get-go. We could have just started with u effective equals the original thing minus this. So we can ignore this too. And so really what we find is that the effective spring constant is just the second derivative of the potential evaluated at the equilibrium, because then it has precisely the correct form. It has the variable minus some equilibrium position, and that is the equilibrium position. That's the place where the object is, where the Earth is moving fastest. It's divided by 2, so it has the correct scale, and we have the correct derivative structure. So now we can just go calculate this. Let's take the derivative that we had before, which was this guy. We'll take one more derivative and then plug things in. We're not setting it to 0 this time. This time we're just evaluating. So one more derivative would give us the second time derivative of the effective potential is, well, we would get a factor of 3 in the numerator, 3L squared over me r to the 4th. And we have a minus 2 gms me r cubed. And then we would just plug in r naught. It's not that it's 0, it's that we can ignore it because it's a constant. Like, we could have just chosen that the, like imagine instead that we had written this minus whatever that works out to be. The point is we can just subtract off whatever, we can always add a constant. And so we just add the constant so that the value is 0. We're just shifting this whole function out. And you can do that because you can always add a constant to a potential energy, where u naught is negative L squared over 2 me r naught squared minus gms me over r naught. That's all. Okay, so that's what our second derivative is, and so we evaluate it at r naught, and I'll spare you the details. What we would find is we would find that this effective potential, the second time derivative is 1.185 times 10 to the 11th. And let's think about the units for a moment. So it should be units of 1 over, so this bit has units of newtons per cubic meter, newtons per square meter. So that means that this should have units of newtons per square meter. By the way I knew that circled bit has those units is because this can be written as gmm over r times 1 over r squared. This has units of newtons, this has units of inverse meter squared. So the whole thing has to have units of inverse meter squared. And lo and behold, these are the units of a spring constant, right? Newtons per meter squared. Those are the units of the spring constant. So this is what our effective spring constant is. And we can go even further, actually. The question asks, how long is one period of this simple harmonic oscillator model, right? And remember, we were able to figure out how long that is by using the effective potential and by using, the effective spring constant and the effective mass. So we just need to go and we need to figure out what the effective mass is. So we already know what the effective spring constant is. The effective mass is just the mass of the Earth. Because in our equation, the effective mass is the thing that multiplies the 1/2 times the derivative squared. So that implies that the period is 2 pi times the square root of the mass of the Earth divided by this effective spring constant. And so you can actually go and just explicitly compute that. And you'd find that this is equal to 365.13 days, which isn't exact, right? 1 year is actually 365.24-ish days. It's off by, maybe a few 10,000ths of a percent, but it's very, very close. And that's why this sort of approximation is good, right? Because we were able to figure all we knew starting out was the maximum distance that the Earth is from the sun and the minimum distance that the Earth is from the sun. And then we noted that those distances are close. So that means that the orbit should be approximately circular. From there, it's just a matter of going through this process, doing a little bit of clever manipulations, like using the effective potential and so on. And we can actually figure out how long a year is just by making an approximation and imagining that the Earth's orbit, at least the radial distance, behaves like a simple harmonic oscillator. That tells us how long a year is. It's 365 days. And we didn't need to know really anything else. Wouldn't K be 2.4?
Wait, where were the units of
time?
Oh,
you're totally right. I'm sorry. I read it wrong off of my. Yeah, you're right. You're right. It should be this times 2.
Wait, where were the units of time in the terms we were plugging in?
Where are the units of what?
Units of time.
Where do we need units of time?
Because T got about 365 days. So where was there anything that had seconds
So Newton's has time built in. So a Newton is a kilogram meters per second squared, and then we divided that by meters squared, and those are the units for the effective spring constant. So that's kilograms per meter times second squared. Then we divided the whole thing by something's not right. Something's not right. Hold on, because the units of distance should cancel out, so I'm making an obvious mistake here. Newtons are kilograms per meter squared. That's true, or a kilogram meter per second squared, rather. So then this should be newtons per meter. Yeah, that was my mistake. Yeah, and that mistake came from me saying that this has units of newtons. It doesn't have units of newton. This has units of newtons. It was just a simple error. So then we get the meters cancel out, so we're left with kilograms times per kilogram per second squared. And then we do kilograms divided by kilogram per second squared, and we're left with units of seconds. Easy mistake to make. Does that make sense? I hope.
I just gotta put this stuff down.
Okay. The final, it's the same person writing the final, so it'll be similar in structure and similar in difficulty. I'll try to tone it down a little bit because I know that people have trouble with it, but today's not the day to be asking questions about the final because I haven't written it yet. Hassan asks, can I go over number 2? So Quila actually asked me how I got the L squared equation again. So that's actually I think in lecture notes 26. It's kind of involved where that equation came from. Let me see if I can find it. I think it's lecture 26. Maybe it's lecture 25. Yeah, it's in lecture 25. It's like halfway through lecture 25. It takes a little bit of work. I can think about deriving it right now if you want. But it definitely takes some work. Yeah, it was it was that equation. The point is, so I used that equation, but you could have gotten the angular momentum a different way. You could have just figured out what the speed is. Oh, okay. You could have just figured out what the speed is. Sorry, it's. Let me get rid of that. So, or let me put it back and let me fix this correctly. So this is true. That is not true. So that's what. No. It should be 2 times that. It's 2 times that because I used a computer and I've divided by 2. That's all. And I read off what I was using for what I used on my computer calculation, which is here. I don't know if you guys can see that, but I read off. I don't know if you can. I don't know how visible that is, but I was just reading off of this number here, and so I just dropped the factor of 2. That's all. There's nothing special going on there. So Hassan asked, go over number 2 really quick. Let me look at number 2. Okay, so number 2 was just a question about energy conservation. So the bottom line was that all this magical spaceship is doing is, in order to get from point A to point B, or to get from, say, orbit A to orbit B, all you have to do is figure out what the energy difference is of those 2 orbits, and then take the difference, and that's how much energy is required. So in part A, part A asks you to find the orbital velocity around the Earth at a particular distance, and I can pull that up for you if you guys want it, but you guys know how to find the orbital velocity at a distance. It's not so hard. So you can find the gravitational potential energy at that distance from the Earth. You can add to it the gravitational kinetic energy that it has because it's orbiting the Earth at that distance. This for part B. And then just figure out, so that would be the energy of that orbit. It would be the orbital energy. Okay, I can rederive this. So the gravitational force. So if the only force acting on so let's say you have the thing you're orbiting, and then you have the thing that's doing the orbiting, moving at some speed v. So the force points this way, and that's the only, if that's the only force in the system, then we get that F net, which is equal to ma. Now this is centripetal acceleration because it's moving in circular motion. So I'll put a c there. And F net in this case is minus gmm over r squared times r hat. And the centripetal acceleration is m, well, the magnitude is v squared over r, and the direction is r hat. It's negative r hat because it's pointing towards the center. So really what we're saying is that, well, sorry, I need a minus sign in front of that r hat. So really what we're saying is that gmm over r squared is equal to mv squared over r, and then you can just solve explicitly for v. So the m's cancel, you can get rid of one of these, and so you're left with that v is equal to square root gm over the distance. That is the orbital velocity at some distance away from the thing you're orbiting. So once you have that, then the kinetic energy is just 1/2 mv squared, and then you add to it negative gmm over r, and so you have r, you have m, g and m are both given to you, or g and m are just the mass and the mass of the Earth and the gravitational constant. This is the mass of the spaceship. This is the mass of the spaceship. You can find the orbital energy. Call it final. Now we want to figure out what is the energy that you have when you're just sitting on the surface of the Earth. Well, The implication here is that you're kind of just sitting still while you're on the surface of the Earth, so you only have gravitational potential energy. So you have minus gmm, and this time, the distance you are from the center of the Earth is the radius of the Earth. So if you want to figure out the difference in these orbital energies, because we're not interested in separating out the radial component of the kinetic energy to the tangential component of the kinetic energy. So the only time that you use the effective potential is if you actually want to separate out those components of velocity. But we don't need to do that here because we're just interested in the total energy. So we take the difference of these two things and you just get a number. And that number, it would be some amount of joules that would be the amount of energy that the spaceship takes to get to that altitude. In part C, you would assume, and this is that whole business with the Hill sphere, the idea is that once you're at that altitude of about 1.5 times 10 to the 9th meters above the surface of the Earth, at that point, you're basically not orbiting the Earth anymore. You're kind of just orbiting the sun with the Earth. Like the Earth's gravity is weaker on you than the sun is at that point. So the sun is the dominant factor. So in that case, we just assume that we have the orbital energy. We have the orbital velocity that the Earth has about the sun, and we have the gravitational potential energy that the sun has about the sun, or at least the same distance. And then you just do the same thing. So the total energy this time, the initial total energy, would be 1/2 times the mass of the spaceship times the velocity of the Earth relative to the sun, plus minus g, the mass of the sun times the mass of the spaceship, divided by the distance that the Earth is from the sun. I'll actually call that Earth. Yeah, I'll just write ES. And you can assume it's a circular orbit because it's very nearly circular. And then if you want to do to find the final energy, this is the orbital energy that your spaceship would have if it were orbiting Mars. It would be 1/2 times the mass times the speed of Mars, because you're moving at the same speed that Mars is as you travel around the sun, because you're sharing an orbit with Mars. Plus, and then you would do the same thing, g times the mass of the sun times the mass of the spaceship times the distance between Mars and the sun. And then you just take the difference again. And what it'll turn out to be is, let me open up, I've done this calculation before. Let me pull that up. I think it's there. Yeah. What you'll find is that the energy to go from the Earth, or the energy difference between the surface of the Earth and the Hill sphere, this is that really far distance away from the surface of the Earth for part B, that change in energy required is something like 6 times 10 to the 4th, or sorry, 6 times 10 to the 11th joules, which is a lot. Like, it takes a lot of energy to get off the surface of the Earth. And then for part C, you find that the total energy is something, or that the energy to go from Earth's orbit to Mars's orbit is like 1.3 times 10 to the 12th joules, which is just to say that, and the whole purpose of this exercise is to compare these two numbers. This one is only like slightly less than half of the energy to get away from the Earth is only slightly less than half of the energy to go from Earth to Mars. And the reason why I had you do this exercise is because it's interesting to think about, right? The amount of energy just to get away from the Earth's influence is of the same order of magnitude as the amount of energy that it takes to go from Earth all the way to the orbit of Mars, which is amazingly far away, like 100 times further away, maybe 10 times further away. And the reason why this happens is because even though the sun's pull is so much stronger than the Earth's pull, when you're starting out at the distance that you are when you're at the Earth, the sun's pull is kind of weak, or rather, you're already really far away from it. So going from Earth's distance to Mars's distance with regards to the sun's pull, it's not a huge difference. Really you're taking the difference of inverse squares. So it's just not a very big, it doesn't contribute a whole lot. And even though you're orbiting around the sun really fast, the change in the gravitational potential energy really kind of cancels that out. And so the bottom line is that, and this is kind of like a well-known truism, in orbital mechanics is that getting a spaceship from the Earth to orbit is halfway to the moon. Like that's another way of putting it. Like it takes just as much energy to go from Earth stationary to orbiting around the Earth in low Earth orbit as it does from going from low Earth orbit to get to the moon. And you know that obviously it's an approximation, but it's still relatively true, and that's made even more difficult by the fact that there's air resistance that you have to overcome when you're launching a spaceship. So it takes a lot more energy to actually get into orbit than you'd think, because you have to launch a spaceship through the atmosphere, and then similarly, you have to not only do you have to just have the kinetic energy associated with the Earth, associated with the orbit, you also have to get to that place, which involves going upwards, so you fight gravity and lose energy that way. No. So getting to Mars takes about twice as much energy as it does to get away from Earth. But getting to the moon, it takes of the same order of magnitude to get to the moon as it does just to get into low Earth. It takes about the same amount of energy to go from low Earth orbit to the moon as it does to go from the surface of the Earth to low Earth orbit, even though the moon is 185,000 miles away. Sorry, it's not 185,000 miles away. It's 1.5 seconds. 224,000 miles away, I think. Maybe 260,000. Well, anyway, some large number of miles. And that's just because getting out of the deep part of a gravitational well is hard, whereas it's a lot easier once you're out of the deep part of the gravitational well, i.e. near the thing that you're trying to escape. It's a lot easier to move around because the gravity isn't nearly as strong. All right, so that takes us through to the end. This wasn't quite the review that I was expecting because I was just answering homework questions. Hopefully it was helpful, though. I know that a lot of the material that we've covered in the last week or two is kind of challenging, so maybe it will be helpful. I will be holding another review on Friday, a more informal review. I won't be recording that one, so if you can't make it, then sorry, but I figure it will be, it's just like, it wasn't originally planned. That's why it's more informal. So I'll stop the recording here and I'll stick around for a few minutes.